It's my pleasure to be here to present our work, which we have done 2 years ago during the COVID-19. So it's very great to have a chance to present this work in person. So this work is a counterexample-guided debugger for non-recursive datalog. This work is done with Professor Gato and Professor Hu. So So this debugging problem for non-recursive datalog is very similar to the general debugging problem. In datalog, we also have a program that has input and output, and we can specify the property of this program by a precondition of the input and the postcondition for the output. And in this way, this raises two very common questions. The first question is for finding a counterexample for the program if the program is not correct. And the second question is how can we locate the detailed bugs in the program. So first, let me give you an example of how a datalog program is written and why the properties for this datalog program is necessary. So this example is from our previous work, which we published in early 2020. And in this work, we provide a new way for using datalog to program various strategies in relational databases. In relational databases, we have many source tables. For example, in this slide, I have two simple tables, S1 and S2. And in relational databases, we usually define several logical view over the source tables. For example, in this example, I define a view which is a unit of S1 and S2. And we can easily read data on the view, but because the view is a logical table, so if we want to update the view, we have to translate this view update to source update. For example, in this here I have a server update to the view, which is an insertion of tuple A4 B4 and the deletion of tuple A3 B3. So we have to insert tuple A4 B4 to the source tables and also delete the tuple A3 B3 from the source tables. So this update translation is not trivial. And it's very ambiguity. So we provide a way to programmers to specify explicitly an update translator. So this update translator is implemented in this very simple datalog program of 3 rules. So if you are not familiar with datalog, so you can think datalog as a block without functions. And this datalog program has 3 rules. The first rule will specify how we can do some deletion from the source table S1. And similarly for the second 2 rules, we specify how we can do insertion or deletion from the source table S1 and S2. The notation minus is for deletion and notation plus is for insertion. So this update translation is not cheaper because we have to specify some property for this datalog program, and usually for view update problem, many people formulate the property as a view update translator as rushing properties. In the left-hand side, if we do no change to the view, so we should have no change to the source. So the update translator should be empty. And for the right-hand side, if we have the view updated and we do translation from the view update to the source update, then we should obtain the same view by using the view definition get over the source, the updated source. And the program have to satisfy the 2 rushing properties, and this is an example of a bugging datalog program. So this datalog program is a bit more has one more rule in comparison with my previous datalog program, because in datalog program usually we may introduce many fresh intermediate relation. For example, here I have one more intermediate relation M. After computing M, I will computing the insertion to the source table S1 from that intermediate relation M. So this datalog program is a update translation. It will take the input of 2 source tables and a view to compute update. In other words, the delta tables of the source. And in this case, the program is incorrect. You can see here the order of two variable x, y is wrongly used. And because of this mistake, we will have a unexpected insertion to source table S2 in the data table of S2. So this is an unexpected point in our program. And so for debugging the dog programs, there are several existing works. For the first version of finding counterexamples, actually, to the best of our knowledge, there's no static approach to statically generate counterexample for the dog program. Most existing approaches will randomly generate many test cases for the dog program with specifications and then check dynamically. So one typical work for this is prop check. It is for prop, not specific to the log, but the log is a subset of prop. So prop check can be also used for the log. And for the second version of locating bugs, we have several approaches. But this work will have some general debugging methods for the log with no restriction. But here we are focused on only non-recursive datalog, and the existing works only give debugging method for datalog program if the counterexample is given. But here we have combination of in our work we will have a combination of one for generating counterexample and one for the debugging engine. And we also allow the user to specify properties of the datalog program. So first, let me introduce how we can specify properties for the datalog program. First, we need a language for that property specification, right? So the thing here is we can still use datalog language for specifying properties or specifying precondition and postcondition of the input and output of the datalog program. For example, in my previous example, this datalog program, first for this property, I will specify the precondition of the input that the view is unchanged. In other words, the view is still the unit of the two source table S1 and S2. And the post condition here is, we should have no updated source. So all the data tables of the source should be empty. And this precondition and post condition can be expressed in the log easily. So for the precondition, where the view must be equal to the unit S1 and S2, we can specify this by using the four simple datalog rules. The first two rules will compute the unit of S1 and S2 in a relation E prime, and then the last second rules have a special symbol in the head. That is important symbol. It means if a tuple of xy in V and not in V prime, there should be no subtuple. And also, similar in the last rule, there's no tuple xy in V, but not in V prime. So in this way, V and V prime must be equal, and then V is equal to S1 union S2. For the post condition, it's easier. We just have three rules that indicate all three data tables must be empty. So that's how we can use datalog to write precondition and post condition for the datalog program. Now I will present our first part. That is a counterexample generator. So as I mentioned before, we have a datalog program with some specifications also written in datalog. Our framework will first validate whether the program is correct or not by using proofs of technique. This is to ensure that we will not generate a counterexample for a correct program. For a correct program, we don't have to do debugging. If the validator fails to prove the correctness of the program, then we will really do the counterexample generation. The validator and the counterexample generation here is implemented on top of some SMD solver. For the first step, for the validation step, we use a standard transformation from non-recursive Datalog rules to first order logic sentence. For example, for this rule, we have a one bracket in head and a bracket in the body. Actually, the meaning of this Datalog rule is a first order logic sentence that the conjunction of all brackets in the root body imply the, the, the head bracket, and all three variables are universally quantified. And then the final sentence of the property of the program is if the precondition is satisfied and the post condition is satisfied. In this way, we obtain a first order logic sentence of the whole properties program, and we can use some expert solver to check whether the program, the property sentence is valid or not. And in the case it's not valid, then we shall do counterexample generation. The idea of this counterexample generation is we shall first encode the input of the data program, which is some relational tables, into some symbolic tables. So instead of having real value for S1, S2, and B, then we have server symbols in the database, A1, B1, and so on. And over that symbolic database, we will encode the evaluation of the data program into some functions. By having the functions, the evaluation functions over the symbolic database, we finally add an assertion to the output of the evaluation. That is, if the symbolic input satisfies the precondition, then the output does not satisfy post condition. And finally, we will solve all the assertions by using Rosette framework. That will give us the concrete values for each symbol in the symbolic input database. And for more details, how Datalog rules can be transformed into functions. So this is a demonstration. This is a very typical Datalog rules with a head and some bracket in the root body. For the positive bracket in the root body, we transform it into Cartesian product, and we add a filter for some comparisons or equalities in the root body, and then the third filter will be used for negation used in the root body. And finally, we call the map function to just select what attributes we are interested in the root head. So here, only two attribute x, z is our interest. And in case relation R is defined by several rules, we just need to gather all the results from each rules by using concatenation, and then we got the output of the Datalog program. And finally, for the rules of the precondition and post conditions, we just need one more step. In the rules of precondition and post condition, we have a special symbol bottom in head. For this bottom symbol, we will use a dummy relation. Here I call empty set precondition. So after having the translation of empty set precondition, we shall add an assertion that this the result of empty set precondition must be empty. We are using function to evaluate this empty set precondition, so it a list of tuples, so the length of that list must be empty. And we have similar way for the post condition, and because for the post condition we add a solve to solving where what is the input, what is concrete values of all the symbol is input, that the length of the empty set post condition is not empty. In other words, the post condition is not satisfied. Okay, so that is how the idea of how the counterexample can be generated. Now I will move to the next part of our work. That is the debugging engine for help the programmers to locate the 12 bugs. So because the debugging is very ambiguous process, In our approach, we shall allow the user interaction in the debugging process. So the user interaction is allowed by a dialog-based interface. So the debugging engine will have the user interaction and will inspect the dialog programs to find which rule in the program is working. Of course, this debugging engine will use our generic counterexample in the previous part. Our idea for debugging is we first need a clear structure of the dialog program. The dialog program is a set of rules, so we don't know which order of rules in the dialog program should be evaluated. So our technique here is based on stratification technique, which is very well-known technique of dialog language. So after this stratification, we shall have a very clear structure of the dialog program. And in this example, which the result is 4 partitions of the dialog program, B1, B2, and B4, which shows order of the rules that must be evaluated in the program. For example, the last rule must be evaluated after the third rule because M, the relation M, is used in the last rule. By having this clear structure, we know that the input is passed to P1 and then passed to P2, P3, and so on until we have a final output, and we have plenty tuples in the output. And the debugging engine will inspect from the last partition to the first partition. At each partition, the engine will predict whether if the input of the partition has a font or the partition has faulty rules. And in this way, it will inspect one by one and finally find where its location about. As I mentioned before, our debugging engine will inspect each partition of the program. At each partition, we have 2 possibilities. The first possibility is we have a font in the input of the partition. To predict what is the font in the input of partition, we use the why and why not data problems technique. That is both in server and it works in database literature. By using this data problems technique, we will know why a tuple in the output of the partition is computed. The second possibility is that we have some wrong rules in the partition. So there are 2 possibilities. We need to predict which rules are wrong or whether we may miss some rules in the partition. Basically, the debugging engine will predict all the fonts and will ask the question to the user to confirm whether the predicted font is correct or not. For more details on how a ground tuple is explained, here I have an example of a ground tuple insertion of tuple B2, A2 to the source table S2. And the data provenance technique will explain how this tuple is computed. And the result is that it is computed by the last rule and is computed by 2 tuple B2, A2 in the relation M and B2, A2 in the source table S2. But the source table S2 is base tables. This is counterexample, so it's correct. So the only possibility for this ground tuple is tuple MB2A2 is wrongly computed. And then in that way, we just ask the user to confirm and continue to inspect why M, the tuple B2A2 of M is computed. And I will skip this part. The basic idea of this explaining missing rule is you just search all the possible proof of the missing tuple. So we have implemented our framework by using a camera, and it has a command line interface. It is integrated with the Z3 and the Z framework for symbolic constraint solvers. And we also evaluate our method by using server multi-debug programs, bidirectional transformations. That is used for the unit problem. And the main properties we are using here is retrieving properties, as I mentioned before. And the results show that many debug programs can be debugged, and the counterexamples for the program can be generated. For some, we set the timeout for our experiments is 1 minute, and for some programs, the counterexample generator failed to generate because it takes more time than 1 minute. And usually, the questions used in the user interface are small, and for some simple programs, we don't need any questions to the programmers because the bug was explicitly located. To conclude my talk, in this work, we have introduced a debugging system to non-recursive Datalog programs. We focus only on non-recursive Datalog because recursive Datalog is more difficult to generate statically examples. And in this work, we have several parts for checking and generating examples. We also design a debugging engine for programmers with dialog-based interface. So thank you for listening.
Impressions. Very effective. Just a quick question.
Yes.
Number one, the stratification restriction of the program, is that important? Or is it just for efficiency? Yeah, that one.
Yeah, thank you for the question. Yeah, I think this specification step is quite important in our debugging system because debug programs maybe have a very big set of rules, and we don't know which rule is computed and which order of rule is computed. So we first, before debugging, we should have this very clear structure, and then by having that clear structures, we can navigate the user to each part of the structure and show the programmers all the possibility of bugs and ask them to confirm which one is valid.
Can you also say a word about encoding into Z3? And is it easy?
Yeah, I think I have one example of
architecture slide when you showed that basically solve
sorry, this is for generating an example, right? You're asking.
Yeah, I just want to have a sense of how you use the SMT solver.
Yes.
Deal with database-like questions.
Yes. So yeah, you can see this example of symbolic input tables.
Okay.
And we encode this as a list of symbolic tuples. Oh. And each tuple is a list of attributes of alternate value, right? Yeah. And then we translate the evaluation of the dog over that list of lists. And then finally add some assertions to the
Okay, thank you very much. No further questions? Shall we end the speaker again?
Thank you very much.